Biconditional statement. So let's actually look at a problem to try and solve one. Biconditional statement. So let's look at actual problem and solve it. Can you write a true biconditional from the given statement? If not, give a counter example. And the given statement that they're referring to is this here. And if I look at it, it's an if-then statement. So I know it's a conditional. So they want to know, can you write a true biconditional from this statement? So from this conditional, can I write a true biconditional? And if I interpret true biconditional, I have to recall that a conditional and the converse. So if it's a true biconditional, the conditional and the converse must be true. So that means I have to basically evaluate this, see if it's true, and then I have to also evaluate the converse and see if that's also true. If both of them are true, then the biconditional itself has to also be true as well. So when it says, can you write a true biconditional, you have to check this is true, write the converse, and see if that's also true. So if I wanted to represent this situation symbolically to kind of, or in notation to see what they're talking about, so I have a conditional. Here's my P. Here's my Q. So my hypothesis and conclusion. And I want to know, is this true? Is it false? Then I have to write the converse and determine if that's true or if that's false. And just to point out, if I notice that this is false, I don't have to evaluate the converse. But if my conditional is true, then I have to write the converse and check if that's also true or false. So once I do that, if they both happen to be true, then the biconditional P if only and only if Q, well then I'll know that's true. So this is all dependent on if these two are both true. So that's the idea behind it. So now let me go back and check, is this conditional true? So it says here, if I have two numbers that are equal to each other, then the absolute value of each number will be equal to each other. So if I have two numbers that happen to be the same, then the absolute value of each number will have to also equal each other. So let me pick two numbers that are the same. So let A equal 3. Let me pick a different color. So if A is, let's be A equal to 3, let B equal to 3, right? So I picked two numbers that are the same. And now I want to check. If I took the absolute value of each one, so the absolute value of 3 equals the absolute value of 3. And just to point out, if you forgot, absolute value, so if I have, my number is 3, the absolute value is basically asking you, what is that distance to 0 if you think about a number line? So how far is 3 to 0? Well, that's 3. So the absolute value of 3 is 3, and same exact calculation gives me 3 again. So I can see that if I happen to pick two numbers that are the same, and I take the absolute value of those two numbers, well, they still don't come out to be the same result. So I can conclude that this conditional is true. So I just evaluated P implies Q, and that came out to be true. Since this conditional is true, that means I have to evaluate the other conditional, which is the converse. So let me write out the converse first. So if, in the converse I can see I have to take the hypothesis and conclusion, which this is my hypothesis, here's my conclusion, switch them up. So I get absolute value of A equals absolute value of B. Then A equals B. So here's my converse, and now I want to check, is this converse also true? So if I take two numbers whose absolute values are the same, does that mean that the two numbers have to be equal to each other? So if I recall, the absolute value is the distance on a number line to 0. And I'm already thinking of one situation such that if I look at the number 3 again, well, I know that that distance to 0 is 3 units apart, right? So if I pick two numbers that have the same absolute value, well, there's actually one more number that has the same distance to 0. That would be negative 3, because if I look at the distance from negative 3 to 0, well, that's also 3 units away. So the absolute value of negative 3 and the absolute value of 3, meaning the distances of these two numbers to 0, are both equal to each other. So let me substitute that here. I just verified that the absolute value of negative 3 is the same thing as the absolute value of 3. Both of these numbers have the same distance to 0. And then if I look at the conclusion though, my A in this case was represented by negative 3, and what I picked for B was positive 3. And I can see that these two numbers are not equal to each other. So since my conclusion is false, I know that this conditional actually comes out to be false. So I just evaluated when Q implies P, and I got false. And in order for me to be able to write a true biconditional, both the conditional and its converse have to be true. Since that is not the case, then to answer this question, can you write a true biconditional? Well, no, I cannot do that. And then it said, if not, give a counterexample. Well, this right here that I just wrote out would be my counterexample, right? Because I have the converse, and this is a counterexample is an example that proves your conditional false. So I picked two numbers such that they had the same absolute value, but if the original numbers that I started with were not the same. That's why this conditional came out to be false. So that's my counterexample, and no, I was unable to write a true biconditional because the converse came out to be false.